So let's start our class today. Today I'm going to go over some homework problems for homework 8, and I will do a summary for the contents that we learned from midterm exam until now. So let's go into before we start, the final exam date is fixed to next Thursday, 7 p.m. So the final exam will be basically similar to the midterm exam. First 2 hours will be closed book and handwritten test, and the next 2 hours will be the coding exam that you can use the internet. Okay. So for the first homework problem, we need to build an autoencoder where the latent space is 10 dimension with the MNIST dataset. So this is just loading the MNIST dataset and naming it. So we need to build autoencoder. So autoencoder is basically, as you know, have a special shape. Like this. So this kind of autoencoder. So our input will be 28 times 28. So maybe by reshaping it, 28 by 28 size of a vector will be created for each image. And first encoder have 500 nodes, I should say. So there is like 500 of these, and second layer has 300 of these. And now we're gonna just like squeeze our original image to 10 by 10 size. So the latent space will be the size of 10. And there is a decoder whose size is just equal to the encoder. So these two layers basically have the same size, and these two layers have basically the same size. So for the output of this autoencoder, we want the same image as to these, okay? So when we put number 1 of an image to this kind of autoencoder, we expect the autoencoder to output 1, okay? So this is how to build autoencoder. So we defined the size of each layer. So for each hidden layer, we defined 500, 310, and 300, 500 nodes. And we're going to use the activation as ReLU. So ReLU is just very widely used, commonly used activation function. And there are other activation functions like sigmoid or tangent H like that. And we're going to use the Adam optimizer to solve this, okay? So this kind of optimizer is up to you, but there's few options you can choose. And we choose the learning rates to be 0.001 and max iteration 50 and tolerance like that, okay? So after we defined autoencoder with this kind of MLP regressor, so basically we use the scikit-learn neural network, but most of times we don't use this kind of scikit-learn package because there are like TensorFlow and PyTorch that can be more flexible than this kind of MLP regressor defined in scikit-learn. So this is just an example. So if you can use your TensorFlow or PyTorch during the exam, then you may use them. And for those who don't know how to use the TensorFlow or PyTorch, you may use the MLP regressor defined in the scikit-learn package. So professor wanted to just not go to TensorFlow or PyTorch in this course because he's teaching the PyTorch and TensorFlow for graduate students. For undergraduate students, professor wanted you to just use some kind of function defined in scikit-learn package only. But if you can use them, if you know how to use TensorFlow and PyTorch, it is fine. So after fitting this regressor multiple times, like this, okay, 50 times as we defined above, and we're going to choose a random image and put in this to put the image, the autoencoder, so that we can see whether it can reconstruct our image well or not. So this is basically choosing a random integer, random number, and we're going to choose a image and put it into our autoencoder. So this is the result, and as you see, the reconstructed image is quite blur and messy, but we still know what kind of this number represents. So I guess the autoencoder is trained widely. Okay, so if you think this kind of autoencoder's performance is very bad, then you may want to just increase the number of layers, or maybe you can use convolution neural network instead of just ANN. So convolution neural network is not in our class, like coverage. So this convolution neural network is basically for images. So you're going to learn when you go on a deep learning. So basically this autoencoder based on ANN is doing pretty good for reconstruction, but still the error is quite large. Okay. So after we moving this 10-digit class to the latent space, we're going to classify that latent space, and we're going to achieve the accuracy. So first we need to make this images into latent space. So latent space is like here. Okay. So why we want to use the latent space? Because as you can see in next problem, if you choose latent space as 2-dimension, you can just visualize your latent space, and so that you can see how those images are clustered in a latent space. So this kind of latent space is for visualization, and with this kind of visual information, you may generate a special image. So this kind of latent space is very important. So since we trained this autoencoder, okay, so we're going to use this coefficient and intercepts to do the to make it into the latent space of 10 dimension. So first we're going to use coefficients and intercept. This is basically omega tx plus b. Okay. And after we done this, okay, this output goes into activation, right? This is basic MLP stuff. So this activation will go into this result function will go into activation, and this is the activation function. This is tangent H activation function. Although we use the ReLU activation function above, but now we're going to use the tangent H activation. And the second layer is also same. We're doing the omega tx plus b on the result of this activation. So basically, this is it's like this. So first, you're gonna x is given, and you're gonna make it omega tx plus b with the first layer, and you're gonna send this to tangent h, which means the tangent h of omega tx plus b is now given, and we're gonna use another. Let's say this is like x. R, okay, and we're going to do omega tr plus b, and we're going to send this to tangent h again, so that we can get the final. So as you can see, we done the same thing, and for the latent is our third layer in our autoencoder. So it's also same using the tangent h activation function. So after we do this, we make all the integers, send all the integers into images into the latent space of size 10. Okay. So after we sent all this kind of images to latent space, so this means that now each of image has size of 10. So originally our image was 28 by 28. And we changed this into a vector size of 10 784 of vector, and we use this kind of encoder to send this kind of 784 dimension into a 10-dimensional latent space, which means now in the latent space every integer is represented in 10 dimension. Okay, and we're going to use this information so that we can to classify our images. So basically, this encoder part is dimensionality reduction that we have done for like 2 weeks or 3 weeks ago. So PCA, like this kind of stuff. So this autoencoder is also one kind of dimensional reduction algorithm. Okay. So we now reduced our 784 dimension into 10 dimension. So after we sent all of image into 10 dimension, we make a classifier, and for the classifier we're gonna use solver as LBFGAs, and this is up to you what to use. And activation, we use logistic activation, and we use ANN of hidden layer size of 50, and learn rate is initialized like that. Okay. So after we define the classifier, we're gonna just train this. After training it, we're going to test our classifier if it can classify correctly or not. So we sent our images to latent space, okay? And this latent space 10-dimensional image will go on to the prediction classifier, and whether you can check whether it predicts correctly or not by using this. So basically this means we're going to use 100 test images, and if first image is correct, we're going to use 1 and add additional number ones if we're making the correct predictions. So out of 100 predictions, our classifier showed that we successfully classified 70 images. So I think the importance of this question is to create the autoencoder, to make your own autoencoder to send this kind of images to 10-dimensional space, and adding a classifier on that 10-dimensional space to classify the images. So one may say, hey, why we are using autoencoder to reduce the dimension and then classify? Why don't we just classify 784 dimension? Well, it's up to you, because I don't know. This classifying 784 dimension by using a classifier may or may not be outperformed using this kind of squeezed image as your input data. So this kind of autoencoder, this example is just to show you that autoencoder can be a tool for dimensional reduction, and we can use that reduced dimension to classify the actual images. Okay. So next is same, but we are using another type of data. This is EMS data, which is handwritten images. So I'm going to skip these parts. Okay. So this kind of images we have. Okay. Okay, first we need to make our own autoencoder. So, okay, so this is basically creating a training data and training label and test data and test label. So I'm not going to go over this kind of process. So this code here is just to make image normalized image. This basically means that every pixel of an image is a number from, I guess, 0 to 255. So we need to normalize this kind of pixels so that we can change into the pixel value within the 0 to 1. So we're dividing this 255 on every pixel of the image, okay? So we can normalize our pixel values from 0 to 1. So our input shape is same as before. And for autoencoder part, we added a layer to the previous example. And this time we're gonna use the two-dimension latent space. As I said before, when we use the two-dimension in latent space, that we can visualize this latent space, which means we can do a lot of things in those latent space, okay? And for the decoder part, it's the same. And we're going to be the autoencoder, and this kind of we have done before, and the same. So we defined all the hidden layer sizes, and we're going to use the tangent H activation function, solver as ADA optimizer, and rest is the same. Okay, after we train this our autoencoder, and we're going to reconstruct a random image. So we choose a random image, and let's see how it reconstructs. As you can see, it reconstructs pretty well, and we can easily see that this is A, Y, and G, okay? So our trained autoencoder is supposed to make like A kind of image into a two-dimensional space, and then make it again to the image of A from that two-dimensional latent space. So basically the first encoder part is for dimensional reduction, and the second part is for like dimensionality expansion, so that we can get the original data. So let's see how our latent space looks. Okay. So before that, we defined our autoencoder manually. Okay. So this is same as before. So our data goes into the first autoencoder, which means our data x going on to omega tx plus b, and also goes into tangent h activation function. Okay, so the same, and the second goes into the result of the first encoder goes into the second autoencoder, and then the result of these go on to the activation function, and the result of this activation function goes into the third layer, and the result of this kind of third layer goes into activation function, and the last term goes into the latent space, so that we can do again, so omega tx plus b, and then we use last activation function to make it two-dimensional space. So with this kind of code, we can reduce our original data into two-dimensional space. So when we choose, when we draw the latent space, it looks like this, okay? So each image goes into two dimensions. Since this is two dimension, we can use the first value as x level and the second value as y. So we can draw a xy plot, so we can visualize our dimensionally reduced part. So as you can see, the A is grouped like here, and G is grouped like here, and Y is grouped like below over there, okay? So by reducing into two dimension, we can just you can visualize very easily. So this question is quite different from others, because this question just assume that we don't have any labels on the test set, which means that we do not know what each points on this two-dimensional space belongs to. Okay? So we're going to have this kind of 2D space with our latent space, 2D latent space. But however, we do not know what each points belongs to a class, okay? Which class. So we're going to use the k-means clustering that we learned like a month ago in order to group these points into separate three groups so that we can classify it, okay? So this k-means very simple with a scikit-learn package. So basically, we just removed all the labels, which means that from this kind of plot, we remove all of these labels, so we end up having this kind of image. So in this kind of image, we need to use the k-means clustering in order to cluster these group points into 3 groups so that we can classify them. So the result shows like this. Okay, it's quite similar to the original answer, but some points are misclustered, I guess. So after doing this clustering stuff, just to show you, we can make this into 2-dimensional space, and then we use the cluster in order to classify this kind of points. So autoencoder, we do not use any kind of label in this kind of autoencoder, right? So in this kind of type of autoencoder, we just put the original image into this input space. However, we do not use any kind of labels, right? So this is unsupervised stuff, so you don't need any kind of label. So you put an image, and you will get an image, but we don't use any labels. So this is quite true. Okay. This kind of so latent space, after you reduce into 2 dimension, because you don't use any kind of label, you will see that kind of space. Okay. However, because you don't know the actual label for each of points, you use a k-means cluster to cluster these points into 3 groups so that you can give them a label. Okay. So autoencoder is unsupervised. You need to know this. Okay. So now we're going to generate fake alphabet decoded from the centroid of each cluster. So this basically means that we reduce these images into 2 dimensions, and we get this kind of output. So this means that each points represent A image in here, and these points represent Y images, and these points represent G images. Okay. So when we choose a random points on this kind of space, then we will be able to get an image that looks very similar to Y. And if you choose a random point on this kind of site, then we can get an image that is very similar to G. So this is basically what it means. Okay. Since the question wanted to use the centroid of each cluster as the point that you need, so you just sum this all xy coordinates and find the centroids of each clusters. So after finding the coordinate of each cluster, we use a decoder. So decoder was basically the same, but the dimensionality is just expanding to original size of 784 from 2 dimensions. Okay. So this kind of reverse of the first encoder part. So 2 dimension to 784 dimension. So these steps are same as encoder, so I'm not gonna just go over it. So after this kind of decoder, you can get after you define a decoder and give this kind of decoder a coordinates for each of centroid, then you will be able to get this kind of images. Okay. So first centroid has we used autoencoder for the dimensionality expansion decoder for the dimensional expansion, that we generated a fake image of A. So we can classify all this C0 integer as A, okay? And the second, we use the centroid of these green points, and the centroid of these green points gave us the Y. So we can say that, oh, C1 class was actually the Y class, okay? So autoencoder does not use any kind of label, so unsupervised, so you can just give the label by doing this kind of stuff. And also, after using the centroid, you can say that C2 is equal to G. So you can generate fake images with this kind of autoencoder by selecting a random point on this kind of latent space, okay? So, autoencoders, as you can see like this, it is also for dimensionality reduction and for the dimensionality expansion. However, in the dimensionality reduction part, you may choose a random point so that you can generate a new image that was not included in image but generated by the autoencoder. This means that if we train autoencoder very well and produce a fake image that is very close to the real image, we can increase the size of the data we have so that we can improve our classifier or regressor's performance. So this example shows that autoencoder is good for dimensionality reduction and good for image generation or data generation so that you can use for your improvement of your model performance. So our question 4. So we're gonna implement autoencoder algorithm for the face data, okay? So our data is just images of this kind of people, okay? And building autoencoder is redundant, so I'm not going to explaining it again. So this is just defining the input size, the encoder, and the decoder size, and latent space is now 8 dimension. As you can see, the latent space, the encoder is very shallow, so 2 layers of hidden layers, and the decoder is just 2 layers, so this kind of shallow autoencoder. However, our image is very complicated because the humans does not share the common features. For example, all these MNIST data or eMNIST data share the same, okay? This is kind of one, and another type of one is like this, so this is very similar. However, this kind of human image is very distinct from data by data, so even if there's like human, they can be a woman or they can be a man, and these 2 types are both human but very different each other. So after we building this kind of autoencoder, we train this kind of autoencoder so that if we given this kind of autoencoder a image of people's face, then it will give exact same images of human face. So autoencoder, if we train autoencoder very thoroughly, then we expect our autoencoder to produce the exact same image. However, as you expected, the test, if we give the test data set into this kind of trained autoencoder, our reconstructed image is very poor. So basically, our autoencoder couldn't fully train the features of the human images. So human images are very distinct to each other. So this kind of dimensional reduction failed because it contains a lot of information to be reduced into 8 dimensions. So autoencoder failed like this. Also, if you put a human image with a head, our result shows that basically blurred image without head, okay? And also the shape of a face is very different, okay? So our reconstruct image is very different from input image, so our autoencoder quite failed in reducing the diverse human image into a reduced dimension and then expanding it to this reconstructed image. So for this kind of problem, you can say there are 2 solutions for this, okay? So first solution is to increase the number of layers, okay? And also the size of the latent space. So, and the second is use CNN instead of ANN. But you don't need to know the CNN, so I'm not going to go over it. But A and N is, as you can see, A and N just you need to first make it as a vector and then use this vector into our A and N. However, by reshaping our original image into the vector space, it just destroys every spatial feature, which means that we know that this kind of section was head, but because we just make it as a one dimension, we reduce all this kind of spatial information. So images are very, very closely related to the next pixel. For example, if you select this pixel, we expect the next pixel to be also eyes. However, by reshaping into the one dimension, we cannot use this kind of information that we have on an image. So using the A and N for image is very poor. Okay. However, CNN is doing better for this case because CNN is very closely related to this space. But I'm not going to go over the CNN. So this is just basic limitation of the A and N because A and N just use a one-dimensional space, so we cannot just use the spatial information. So one might say, hey, the human face, okay, this is we checked that our A and N does not work, but for the images for digits or alphabets worked pretty well for the autoencoder. So what is the difference between the autoencoder for the alphabets or digits to the human face? Okay, first, human face is much more complicated, and also in the image like 0 and versus 1. This is quite easy for autoencoder or A and N to classify these kind of two images because in the 0, these pixels are all zeros, okay? However, in 1, there's a straight line in this pixel. So after we vectorizing it, we're gonna see this portion like here. If we say this is like 784 vector space, and some part here that represent the middle of this our image has all zero values. So this one 0, 0, 0, 0. However, in here this will be 1. Okay, so 1, 1, 1, and 774. So after if we compare this kind of vector, this portion of the vector, we will be able to easily classify 0 and 1. So this kind of alphabet is very simple because there is like spatial difference between 0 and 1. So A and N can simply find out this kind of difference even if it is sent to a one-dimension space. However, since human space is much more complicated than this kind of number, we cannot do that. So when we give this kind of sunglass image into our autoencoder cannot reconstruct our sunglass or even the human face. Okay, so our autoencoder fails when we use the complicated data, and for these reasons, this is the limitation of A and N. And for images, CNN is much more better, but CNN is not covered in this class. So any questions for these coding problems? Okay. So now I will give a short summary from midterm exam to now. So this summary is my summary that I used for studying this class when I was taking this class. So our first section was K and N and decision tree. Okay. So we go over the supervised learning. Okay. So what is supervised learning? So supervised learning is given a training set of x1, y1 of xn, yn. So like this. So x represent the image, if you say image, and y represent the label. So each image contains a label. So this is a supervised learning. And in a supervised learning, we want to find the learning parameter omega. So any kind of learning parameter omega, so that if you say f of omega of xi is given, then we want this f function, some kind of function. We're going to define this function as more k&n or decision tree or a and n. This kind of function to produce some kind of label yi. Okay. So we are building this kind of function by learning the parameter, so that if we given an image into this kind of function, that this function outputs a label. Okay. This is basically supervised learning. So we can define a loss in a supervised learning as loss. This is also a loss function. As f xi yi. Okay. So this basically means that since this is supervised learning, we have original label yi, and we know the predicted label by using this kind of function. So we're going to compare these two so we can get our loss, and we want to minimize this loss so that we can train our data. So we can say this minimization of problem is minimize Okay, so this is supervised learning. We want to minimize for all of the image that we have, and minimize the difference between the original level and the predicted level for all of the training image we have. So this is basically supervised learning. And for K&N regression, so this is like regression is basically finding a numerical value for each data. So what is K&N? So K&N is K nearest neighbor. So if we have like data over here, and if we are given a new data or test data from here, and we will use the like 4 K&N, 4 nearest neighbors, then we will use this 4 points in order to define this points label. Okay. So in a regression task, we're going to use the average value of these 4 points as this kind of label. And for classification, we're going to use most abundant class for this kind of label. For example, if this points had a class level of 1, this have 0, 1, 1, then we can choose this numbers label as 1. Okay. So this is just basic algorithm for K&N regression. And for the decision tree, this is very important. So for decision tree, you need to know the disorder and quality of test. So disorder was defined as disorder D is defined as minus x log 2 x minus 1 minus x log 2 1 minus x. So this is basically equal to minus g over t to b over t. So this g represents just good, and this is just example, and b just represent bad, and t is just total. It's just an example. So so we need to find the homogeneity, and for homogeneous cases, the x goes to 0, which means 0 over t, and this will give us zero disorder. And for inhomogeneous cases, then we will have g is equal to b, which will give us x over g over t is equal to 1 over 2, and d will be 1. This order will be 1. Okay, for perfectly inhomogeneous cases and for perfectly homogeneous cases. So this order 0 and 1 is the difference. And then we learned the quality of test. I think the quality of test and the disorder part was part of your homework. So I hope you guys know this. So Q is a quality of test is sigma over D over set times. Okay. So based on this quality of test, so we need to use the disorder computed here and do the quality test to choose whether each feature is good for the decision tree or not. So this is basically doing a quality test of a feature, whether that feature will be important for the decision tree or not. Okay. So if our Q is small, then it's good. So this is KNN and decision tree, and this decision tree algorithm is very simple algorithm, but we don't commonly use this single decision tree in order to decide our label. So we use multiple decision tree. You say that we ensemble the decision tree so that we can have random forest or some kind of stuff. This is just basic because we don't normally use this decision tree as our machine learning, but random forests and or other algorithms based on the decision tree in order to do the classification. So this kind of random forest and other methods is just ensemble of decision trees. And decision trees, in the decision tree part, most important thing is disorder and quality of test. So I expect you guys to do the quality of test on the features for the decision tree. Okay. And for clustering, k-means clustering, I mean. So k-means clustering is unsupervised, as I said before. So if the data is given in this kind of dimension, all the labels are not given, you need to cluster these points so that you can give a temporary label to each of these class. Okay. So let's say if you do the k-means cluster, it will give a C0, C1, C2, because this is unsupervised learning. And if you pick a centroid for each of cluster and just look at these kind of points, you will be able to define each classes by yourself. Okay. So the k-means clustering is basically unsupervised learning, so clustering from unlabeled data. Okay. So normally for k-means clustering, these two are given. Okay, first is M of unlabeled data, and second is number of partitions K. Okay, so you're given M unlabeled data and K partition. So M number of data and 3 or K partition in order to group this data into 3 groups. Okay. So good clustering is achieved by 2 conditions. First condition is higher within cluster similarity. Okay. Conditions for good clustering: high within cluster similarity. So this basically means that within each classifier, all data points should be very similar. Okay. And the second is low inter-cluster similarity. So low inter-cluster similarity basically means that numbers of data from each cluster should have a low similarity. So if our B class 0, which is B images, are here, and C images are here, this kind of 2 clusters should be not similar to each other. So that this means that we do the cluster very good. So this is 2 conditions for good clustering. So the k-means algorithm starts by defining the number of partition K and the data. And for the k-means clustering algorithm, we randomly initiate a point. Okay. So we know from this image, this kind of image, we know the centroid. But if the centroid was not given, then we will have to randomly initialize any kind of points in order to find the centroid of the cluster. Okay. So we're gonna first hey, this is the centroid of first images, and this is second, and this is third, and see whether this randomly selected centroid can cluster the data very correctly. So if you select this kind of points, and then use the dimension, this kind of stuff to group your data, and we're gonna just calculate all the distance from this point to the data, and we're gonna choose we can get the average distance from this centroid point to this all data, and calculate this average distance as our metric. Okay, so for iteratively, we're gonna choose random points differently so that we can cluster this kind of data until we achieve the minimum size of average distance. Okay. So our output of this k-means cluster will be the labels for each of these unlabeled data, and also the average value and of points assigned to the cluster, which means that after we assigned 3 centroids, we can get label for each centroids, okay, each clustered points, and also the average distance from all the points that belongs to a centroid. Okay, this kind of distance is calculated. So you can get 2 things out of k-means. First is the label, second is average distance from all points to that centroid. Okay. So this k-means clustering has a very serious initialization issue. So k-means is very sensitive to the cluster center initialization. So bad initialization can lead to poor convergence speed and bad overall clustering. So there's a safeguarding measures. First is choose center as one of the examples, and second is the farthest from the sample, and the third, which is the farthest from both. This basically means that in order to initialize our K-means clustering algorithm, we need to first choose center of one example, and then second is farthest from the farthest from the first point, and then the third point will be farthest from both, which means like here. So when we choose a random centroid at a example here, then we're going to choose the second point as farthest point, and then the third as the farthest. Okay. In fact, let's write like this. So this is here. If data are clustered like here and here and here, so if we choose a center of our example, and the second is here, farthest from our data. I mean here, maybe, okay. And then we're going to choose the next third point, farthest from all of these 2 points, okay. Maybe here, okay, or here, okay. So we're going to start from here so that we can find this kind of 3 points, okay. So this is just a safeguarding measure, I think, that is stated in the lecture notes. Okay. So in the K-means clustering, the concept of elbow point appears. So for this kind of problem, there's a number of partition K was given. However, if that number of K of partition K was not given, one way to select for K, for the K-means, is to try different values of K, which means 1, 2, 3, 4, 5, and then plot K-means objective versus K, okay? So number of K, like 1, 2, 3, and this K-means objective. In my knowledge, this is just average distance between a cluster centroid to all of the points, and you need to check this, okay? So as you plot this kind of graph, in certain number of K, this should be an elbow point. So elbow points is defined as non-linear shift from non-linear decrease from the linear decrease, okay? This is just the elbow point. So we use that elbow point to decide the number of K when the number of partition was not given, okay? So this this K-means clustering have some kind of few limitation. This first is hard assignment of points to cluster, okay? This hard assignment means that a point either completely belongs to a cluster or not, okay? Belongs at all, okay? Which means that if you do this kind of like, if you choose this point, so in the statistical mind, we say, hey, it is more likely to be in this cluster rather than this cluster. However, in the K-means, hey, just this point just belongs to here and does not belong to here at all, okay? Basically, this means that this K-means algorithm does not consider any kind of probability when clustering the points, okay? This is just a hard assignment. So which means that no notion for the soft assignment. The soft assignment is using the probability, and also that this K-means algorithm is very sensitive to outliers, okay? So if there was 5 outliers that was like here, then our cluster will be shifted to here because our K-means cluster consider the distance from that centroid to all other points, okay? So even if these points are outliers, our K-means cluster will consider this kind of outliers when deciding the centroid, because this kind of outliers is very far from our original data space. So these outliers will have a huge impact on our K-means clustering algorithm. And this K-means algorithm work very well for rounded shape and of roughly equal sizes and density cluster. This means that As you can see here, our data is quite clustered quite roundly, and also it is quite dense. However, if our data is like star-shaped or something like this, and this is very hard for k-means clustering to cluster these kind of points. You cannot just cut our stars into like this. Okay, this is very hard for the k-means to do that, and also it works badly for the cluster that have non-convex shapes like that. Okay, so this is just a few limitations of k-means clustering. And the second to last section is dimensionality reduction. So why do we need to do the dimensionality reduction is we need to get insight from the low dimensional structure in the data. So this is basically for the visualization, okay? So if you have fewer dimension means less chance of overfitting, and this overfitting issue is quite serious in the society of machine learning and deep learning, because our data is small, but our model is too big. Then our model is just simply just memorizing all the labels that belongs to each input. Okay, which means the overfitting means like this. Okay? In 2D space, our data was like our data looked like this, okay? And our insight will say, hey, our regressor should look like this, okay? However, when overfitting occurs, our model just learned very, very wisely like this, which will provide wrong answer if you select this kind of points, okay? So this is a very serious overfitting issue. So we need to make this input data into low dimension so that we can minimize the effect of this kind of overfitting issue. And also with the dimensionality reduction, as you can see with this autoencoder example, we reduced the dimension of 784 to 10 dimension, which means that we can speed up on a learning algorithm, and most algorithms scale very badly with increasing the data dimension, which means that by doing a PCA or something to reduce the dimension of 10 or from 784 to 10, this 10 feature space is very simple and very light to do, okay? For example, in my knowledge, the Gaussian process regression, this is just a type of regressor, you don't need to know. This regressor computes inverse matrix of, like, if data was 10 by 10, oh no, if data was 100 data and 10 space, this Gaussian process regressor just compute the inverse matrix of this kind of stuff. And this calculating inverse or covariance matrix for all this kind of data matrix takes too long time. So we need to just minimize this data space into 2 so that our computation is much more faster than before. It's just an example. And also the storage issue is also, of course, data compression with PCA is very important. So dimensionality reduction is just like feature extraction, okay? As you can see, from the 784, we can choose the 10 space as our input space to classify, as we've done before, okay? So dimensional reduction is just creating a new feature from original feature. Okay. So PCA, we're gonna first dimensional reduction algorithm was PCA. So PCA is used when we want to project our we want projection that captures the maximum variance direction, which means that if our data was like this, and the maximum variance will be like here, okay? So that will be our first principal component, okay? So the definition of principal component is the direction of the vector that maximizes the variability in the data, which means maximize the variance in the data, okay? So PCA algorithm is, so we learned the PCA algorithm in mathematical viewpoint, okay? How to compute the PCA mathematically. And I think this is very important. So PCA for mathematical process, I'm not going to go over because we don't have any more time. So you need to first study about how PCA algorithm works with a matrix, okay? So one thing I want to tell you is the difference between the linear regression and the PCA. So, like this. If data were given like this, yeah. So when we do a linear regression on this kind of data, our result will be like this. And if you do PCA on this kind of data, our result will be also in this shape, okay? So what will be the difference between the PCA and linear regression? So in linear regression, we just minimize this distance, okay? This vertical distance. Because linear regressor just want to make each point's prediction as closely as possible to the original data. So linear regression just minimizes this kind of term, okay? However, PCA in a PCA algorithm, it does not consider this y vertical distance, but it considers a real vertical distance from this principal component to that point, okay? So PCA considers this vertical values that is vertical, perpendicular to its own principal component, okay? So this is the difference between linear regression and PCA, okay? So first, linear regression wants to reduce the error in the y distance. And for the PCA, you want to reduce the error from that from in the direction that is perpendicular to this u, okay, or principal component. Okay. So our last chapter was the ANN and also the autoencoder. Okay. So ANN, I think we know how to do the ANN. So. Yep. Distance. So ANN is basically a multiple layer of perceptron. So there is a concept of perceptron. And if you just stack these perceptrons, you will be able to create a layer of ANN. So, for example, we defined in the autoencoder part like 500 nodes. This means the 500 perceptrons are in this kind of one layer. So in the perceptron, that involves omega. So perceptron is basically if x is given like this, and there will be omega term here, omega t term here, and there will be plus b term here, and this goes into the activation function. So x is omega tx plus b going on to the activation function, and for activation function you may choose tangent h, sigmoid, or some kind of that stuff. Okay. So perceptron, you need to know the definition of perceptron and how the perceptron makes the classification or that kind of stuff. And for the perceptron, you need to know how the update of the weights works and how the iteration of this perceptron is basically working. Okay. Okay. So when you study for your final exam, and if you have any question regarding this kind of contents, please contact me so then I can tell you about it. Also, I recommend you to solve the practice problems that were presented in our website of our laboratory, because some questions that were not given in homework is very important. So if you have solved it and if you ask answer after you're solving the problem, after you just send your answer to me, then I will make sure I can tell you that answer provided by you is correct or not. So I recommend you to solve those questions in PS practice question, okay? So, any questions about final exam? Nope, okay, see you next week then.